Hello everybody and welcome to yet another math video. In this video, I will be going over rational functions. And if you are in one of my college algebra courses, this corresponds to section 3.5. You guessed it, about rational functions. In this video, I'll be going over new stuff like vocabulary. What does a rational function look like? Asymptotes, holes, all of the fun new things that we're going to be looking at regarding rational functions. Then I'll go over how to find vertical asymptotes, holes, and the domain of this type of function. And more broadly, vertical asymptotes and holes are called restrictions, and they restrict the domain, so how they're all related. Finding horizontal asymptotes, and then graphing the rational functions. Yippee skippy. Okay, on this slide, I am going over a lot of vocabulary. You can see there's a graph here. Rein it in, everybody. Here we go. Rational function, that's what we're talking about. A rational function is a function that takes the form of f of x equal to p of x over q of x. Now, what makes a rational function is that these p of x and q of x functions are polynomials. And as always, if you have any variables in the denominator of a function or in the denominator of a fraction, the denominator is not allowed to equal 0. And that is where the restrictions come into play. What types of restrictions do we have? Well, we have two different types of restrictions on the domain. The first being an asymptote, and the second being a hole in the graph. So an asymptote is a line that a graph approaches. So to give you a better idea of what that means, you can see this picture over here. An asymptote, or rather the graph here, is in blue. So these little curves here are what we would call the graph of a rational function. To help with the graphing of this rational functions, we often find the asymptotes of a rational function. These are the dashed red lines you see going across, we'll say horizontally, and vertically through this coordinate plane. And as you can tell, when the graph moves further and further left, it gets closer and closer and closer. It approaches the horizontal asymptote. And as we move further and further right along this graph, this branch approaches the vertical asymptote. And it's the same thing with this branch over here. If we move left on this branch, it approaches the vertical asymptote. And if we move to the right, this branch approaches the horizontal asymptote. So that's what asymptotes are. It's just they kind of like tractor beam the graph toward it. A hole in the graph, I'm going to say, is relatively obvious. It's right here. This is a hole in the graph. We're going to talk more about that a little bit later. But the restrictions on the domain are holes in graphs and vertical asymptotes. So this particular vertical asymptote here has an equation of x equals -3. The hole in this graph has an x value of +2. So really quickly, if I wanted to write out the domain for this function, I would write out -∞, because the domain of this function, the graph of this function, will continue forever to the left. But there's a break in the domain right here at -3. So let's see, that would be at -3. Then there's another piece of the domain here between -3 and 2, because this hole in the graph makes a break in the domain. And then we would have a last break in the domain, or the last piece of the domain from 2 to infinity. And when you have all of these intervals, -∞ to -3, -3 to 2, and 2 to infinity, you have to join them all together with unions. So this would be the domain for this graph of a rational function below it. And again, we will look more into that in the upcoming slides. On this slide, I will go over how to find and classify restrictions. And then we can also use that to explain what the domain of this function is here. Again, rational functions is a function that has a polynomial in the numerator and denominator. And I promise you these are polynomials, they're just factored. And before I go too much further, factoring the polynomials in a numerator and denominator of a rational function is a really good first step. It makes graphing and finding intercepts and finding restrictions so much easier. Speaking of restrictions, in order to find the restrictions, you need to set the denominator equal to 0 and solve before any reducing. So you may have noticed here there's an x minus 2 factor in the numerator and denominator, and yeah, we will reduce those before long. But you can't do it before you find the restrictions. The restrictions are going to be the first thing you find when you're looking at rational functions. So if you take these x minus 1, x plus 3, x minus 2 are not equal to 0. Okay, so that is something I need to change up here. In the definition, the restrictions, you set the denominator to be not equal to 0. Go back and look at the red definition for rational function I had on the last slide. It's where the denominator does not equal 0. Okay, so with that, you can set each of these little factors to be not equal to 0. And we get this. We get x cannot equal positive 1, x cannot equal negative 3, and x cannot equal 2. Those are the three values that are not allowed of all the x values that we have choice of. All right, that being said, we can now classify these. And it's as easy as looking as to whether or not a factor in the denominator can be reduced. So I'm going to start here with x minus 1. X minus 1. And I look in the numerator and I'm looking for a factor of x minus 1. I don't see one. So this factor cannot be reduced, aka canceled, with anything in the top. What does that mean? X not equal to 1 tells us that there's a vertical asymptote. Oops. So this tells us there's a vertical asymptote, we'll abbreviate VA, at x equals 1. The next one, x is not equal to negative 3. That corresponds to this particular factor, right? If you set that equal to 0 and solve for x, x can't be negative 3. Now I'm looking in the numerator. Are there any factors of x plus 3 up here? No. So this will not reduce, which means that there will be a vertical asymptote at x equals negative 3. Last one. I see over here, this is x is not equal to 2. That came from this last factor here. So I've got this one. And I'm looking in the numerator. Do I have any other factors of x minus 2? I do. I do. You saw it. I mentioned it already. Since these reduce, what that does is it generates a hole in the graph. And we can just say a hole in the graph at x equals 2. So the short story of it is, if there is a factor that cancels with 1 in the denominator, that produces a hole in the graph. If the factor in the denominator does not cancel, that creates a vertical asymptote. Okay, so let's take a look at the domain here real quick. Basically, all you have to do for the domain is make sure that you line up these numbers in order, left to right, like you're working on a number line. So if we have a number line here, and I know negative numbers are to the left of positive numbers, I know 1 is less than 2. So here are all of the restrictions I have. To find the domain, you throw out all of the restrictions and you keep everything else. So negative infinity to negative 3 would be the first part of the domain. Essentially, we're just writing intervals that are between all of the restrictions. So this would be negative 3 to 1. This would be 1 to 2. This would be 2 to infinity. Right, so everything to the left of negative 3, everything between negative 3 and 1, everything between 1 and 2, and everything to the right of 2. But once again, if you have all these different intervals, you string them together with unions. And one last thing to point out, if you'll remember that the domain is the set of all x values that are allowed, this even makes more sense. We can pick any x value as long as it's not negative 3. So we use these parentheses around the negative 3 to exclude it. We can pick any x value along this number line as long as it's not 1. So we put parentheses around the 1 to exclude it. And the same thing with 2, parentheses around this 2 because it cannot be number 2. Horizontal asymptotes, HA. So we have vertical asymptotes and we have horizontal asymptotes. Horizontal asymptotes are based upon the degrees of the polynomials in the top and the bottom. So there are only 3 scenarios that you can come up with for comparing 2 whole numbers. Remember, the degree is the highest exponent of the variable in that polynomial. The degree on the top can be less than the degree in the bottom. The degree on the top can be greater than the degree in the bottom, or they can be equal to each other. So let's think about this. If the degree in the bottom is bigger, we could call this bottom heavy. Let's say, there we go. And what happens if the degree in the bottom is bigger? The horizontal asymptote is y equals 0. If the degree in the top is bigger, you guessed it, we would probably call this top heavy. We would say no horizontal asymptote. And in other courses, you may hear the word oblique. And that's where I teach. That's more of a pre-calculus idea. So we just teach our college algebra students to say, hey, there isn't one. And that's true. There isn't one. It's got a slope. It's not horizontal. All right, the last one, when they're equal to each other, we would call this balanced. And what the horizontal would be, asymptote would be equal to is y equals the leading coefficient of the top divided by the leading coefficient, of the bottom. And what do I mean by all of that? Well, the leading coefficient of the top is the number in front of the term with the degree in it, and the leading coefficient of the bottom, the same thing. We just take the ratio of those leading coefficients and we can find the equation of the horizontal asymptote. one last thing, and I did not point this out with the vertical asymptotes. Horizontal asymptotes and vertical asymptotes have to be entire equations. Horizontal asymptotes are always y equals, because that's how horizontal lines work. They're always y equals. Vertical asymptotes are always x equals some number. Make sure you're writing the entire equation. Okay, 3 quick examples on how to find horizontal asymptotes. This is how rational functions would normally be looking. You can see it's a polynomial, nothing is factored. All right, so to find the horizontal asymptote, you have to find the biggest exponent for x in the numerator, that's 2, and the biggest exponent of x in the denominator, 1. So those are the degrees. The degree in the numerator is bigger than the degree in the denominator. I would say this is top heavy, and that means no horizontal asymptote. Pretty simple. Next, g of x equals all this mess here. And you're looking for the largest exponent in the numerator and the largest exponent in the denominator. Oh, and they're the same this time. All right, so this is balanced. So the horizontal asymptote here would be y equals, and we have to take the leading coefficient for each, the numerator and denominator. So the number in front of this degree is -2, and that goes in the top because that -2 is in the top. And in the denominator, you have this number, -13. Ooh, I don't like this though. The negative over the negative, we can reduce that. Negative divided by negative is a positive, so we can just write y equals 2 over 13. There we go. That's the horizontal asymptote there. In the last example down here, we have a 4 degree in the numerator and a degree of 5 in the denominator. And that is what we would call bottom heavy. And if a rational function is bottom heavy, the horizontal asymptote is y equals 0. Real quick on the slide, a good way to find all of the characteristics you'll need for the graphing process and then the actual graphing process. So the first thing you'll want to do is find restrictions in the domain, and within this step you want to be able to classify whether or not a restriction is a vertical asymptote or a hole in the graph. Then you want to go through and find x and y intercepts. You want to find the horizontal asymptotes. After that, you want to just very briefly check to see if the graph has any symmetry, be it or asymmetry through the origin or symmetry about the y-axis or even or oddness of a function. And then lastly, you want to actually graph the function. And how I like to do this is you'll plot the vertical asymptote, horizontal asymptote, x and y intercepts, and you'll plot the domain above the graph. Then you need to make sure that there's a point plotted, a non-x-intercept point plotted in each interval. Then you can draw in the asymptote hugging curve and then put any holes that you may have found in this process up here. You can just put the holes on the graph. All right, first example here, we need to find all of the restrictions here first. So again, the restrictions, that happens when you, set the denominator to be not equal to 0. So that tells you x cannot be 1, and that's either going to be a hole in the graph or that is going to be a vertical asymptote. Well, this one's a little bit tricky here, so we have to actually do a little bit of factoring. X plus 2, there we go, x minus 1. All right. So this factor of x minus 1 from the denominator does not cancel with a factor in the numerator. So that means there will be a vertical asymptote at x equals 1. All right, so there's that. The domain then, since x is not allowed to equal 1, and that's because there's a vertical asymptote at 1, the domain then, if you think of the number line, start here at 1, it can be anything but 1, which means you can be to the left of 1, so negative infinity to 1, or you can be to the right of 1, say 1 to infinity. And for every interval you have, remember you have to join them together with a union. So here is the domain, negative infinity to 1, union 1 to infinity. All right, next we have to find the x and y intercepts. Okay, so the x and y intercepts here are found exactly the same as you have found x and y intercepts before. So the x-intercept would be what happens if you set the functional part of this equation equal to 0. The x-intercepts, the y values are 0. And if you remember from way back when, f of x and y are the same values. So we can just substitute 0 in for the entirety of f of x. So we'll have 0 equals 2x plus 4 over x minus 1. One of the first things you do when you're solving a rational equation is to find the LCD and multiply all the terms by an LCD. So the LCD here would be x minus 1. That would cancel here. And if you multiply by x minus 1 on the left side, 0 times x minus 1 is 0. 2x plus 4. And what this effectively does is it tells you, hey, you can find the x-intercept by setting the numerator of the function equal to 0 and solving for x. So it would be something like this. This part is good for x-intercepts, and this part down here is good for, we'll say, holes and VAs, vertical asymptotes. And all of those have to deal with x's. Think about it. If you set the top equal to 0, you're solving for x. If you set the bottom equal to 0, you're solving for x. Those are all x-related characteristics. Back to the x-intercept. If you solve this for x, you'll get x equals negative 2. So here's your x-intercept, negative 2, 0. The y-intercept, on the other hand, will use the entire function. Basically, you're finding f of 0. So that would be 2 times 0 plus 4 all over 0 minus 1, which is negative 4. So you have an x value of 0, you have a y value of negative 4, so 0 comma negative 4. There is the y-intercept. All right. Next piece, you have to find the horizontal asymptote. And so the horizontal asymptote here, this looks like it is a balanced equation or balanced function. We have a 1 in the top and the bottom as the biggest exponent. When you look at the numbers in front, you get 2 over 1, which is just 2. So the horizontal asymptote here is y equals 2. As far as the symmetry is concerned, you have to go back and look at what happens when you find f of negative x. So that would be 2 times negative x plus 4 all over, what happens is negative x minus 1. So when you simplify this, it's negative 2x plus 4 over negative x minus 1. How do you find the symmetry of a fraction? Oh my goodness. All right. So you have to look at the top and bottom separately is what's happening here. If you end up with an even polynomial over an even polynomial, or an odd polynomial over an odd polynomial, then the fraction is even. If you end up with any mixture of those two, say odd polynomial over even polynomial, or the even polynomial over an odd polynomial, then the fraction is odd. Now in this case, the top polynomial is neither even nor is it odd. And as soon as you find one of the polynomials, either the top or the bottom, that is neither even nor odd, then this function has no symmetry. Again, the only way you can have symmetry is if the top is even or odd and the bottom is also even or odd. As soon as you have a polynomial on the top or the bottom that is not either even or odd, then the function, the entire function itself, will have no symmetry. All right, so we have all of this important information here. Let's use it to graph this function on the next slide. On this slide, we've got all the pertinent information listed out here: the vertical asymptote, horizontal asymptote, x and y intercept. There were no holes or symmetry for this particular function. So the first thing we're going to do is I'm going to make the vertical asymptote. I'm going to put it here. And yes, you'll make it a vertical line and it will be dashed. And then you can label it to VA x equals 1. Cool. I'm going to come along and make sure the horizontal asymptote is there. That's y equals 2. I'll label that HA y equals 2. You can put the x-intercept on the coordinate plane. You can put the y-intercept on the coordinate plane. And there are no holes or symmetry, so we don't have to worry about that. And we can get to drawing the asymptote hugging curve in a moment. The one thing that I haven't done yet is put the domain as part of this graph. And this is how I like to do it. Wherever I see a vertical asymptote, or wherever I happen to have a hole in the graph, I'm just going to draw a union right above it. From there, I know that I can be anything to the left of 1, which looks like this, or anything to the right of 1, which looks like this. Now in each interval, I have to make sure I have a point that is plotted that is not an x-intercept. So it looks like to the left of this vertical asymptote, I have an x-intercept, but I also have this y-intercept. This is not an x-intercept, so we have enough points plotted to the left of this vertical asymptote. But to the right of this vertical asymptote, there are no points plotted. So we have to pick a value, pick an x value, either 2, 3, 4, 5, pick your favorite. Normally going 2 away from a horizontal or vertical asymptote is sufficient. So I'm going to pick 3. And I'm just going to come down here and call this my extra point, because we got to have something there, extra point. And I'm going to figure out what is f of 3. F of 3 is 2 times 3 plus 4 all over 3 minus 1. In the numerator, that's 10. In the denominator, that's 2. 10 over 2 is 5. So I have my x value, I have my y value, and that's the point that I'll plot over here from my extra point. I've got to switch over to a different color. So 3, 5 right here. From there, you can draw your asymptote hugging curve. How does that happen? Well, remember, when a graph gets drawn with asymptotes, the graph gets close to the asymptotes. It starts approaching the asymptotes. So here, it starts getting close to the horizontal asymptote, but will not cross. There's this weird thing about math. You have to connect the dots that are on the same side of a vertical asymptote. So this green dot has to be connected to this yellow one. And a graph will never, ever, ever, ever pass over or cross a vertical asymptote. So this will just keep going down, down, down. So there's one branch of the graph. The other branch, we only have 1 point. What are we supposed to be doing? How do we figure this? Well, for college algebra purposes, the graph will only cross an asymptote in a very specific case covered in a later example. That's not this example. So we just get close to this asymptote and we get close to this asymptote. That's it. You're done graphing. Let's take a look at a few more examples. You get another example here. The first thing you want to do when you're working with rational functions is find the restrictions. So here we have 2x plus 1. If you factor the denominator, you'll get 2x plus 1 all over, 2x plus 1 times x minus 7. And you'll notice that these two factors here can cancel. That tells you there will be a hole here. This x minus 7 does not cancel, so that will be a vertical asymptote there. So we know already that the vertical asymptote will be x equals 7. And that will have a hole in the graph wherever you set this factor equal to 0 and solve for x. So if you solve this for x, you'll get x equals -1/2. That's where the hole is for this graph. Now, to answer the rest of this, the rest of these characteristics, what needs to happen is we need to write a simplified function over here off to the right. So a simplified function here would be 1 over x minus 7. All right. Now we can go through and do everything else. The x-intercept is when you set the top equal to 0. So top equal to 0 is now 1. And if you set 1 equal to 0, that doesn't make any sense. 1 does not equal 0. This would mean there is no x-intercept. All right, so there is no x-intercept. We can take a look at the y-intercept. The y-intercept you can find in any of these functions here. It doesn't matter. You can take the ratio of the constants in this fraction here. You can substitute 0 in for x here. Or you can take the ratio of the constants over here. The constant in the numerator is 1 and -7. They all match up. So the y-intercept here, the y value would be -1/7. Let's see, the horizontal asymptote also works in any of these fractions. You'll notice the original is bottom heavy. And after you reduce, the new fraction is also bottom heavy as there are no x's in the numerator. So the horizontal asymptote here is y equals 0. As far as symmetry is concerned, again, same thing. You can work with any of these fractions. I have not said this yet, but I would generally work with this one over here because it's very easy to work with. The top portion of this fraction is what would be considered an even function, and the denominator of this fraction is neither even nor is it odd. So if you have a side of a fraction that is neither even nor odd, there is no symmetry. So this has no symmetry. And lastly, the domain. Again, remember the domain, we have to just make sure we have the holes and the VAs represented on a number line in the correct order. So it would go from -infinity to -1/2. Union -1/2 to 7, union 7 to infinity. All right, let's see how to put all this stuff together and make a graph. All right, took all of the important information here from the last page. We need the intercepts, the asymptotes, the holes, fine. We've got all this work down here, there's no symmetry. All this done over here already. We have the domain listed at the top. That looks good. All right, so what? We have all this stuff down. We need to make sure that we have a point plotted in every single side of the domain, or in every single interval of the domain. So you can see this one is in this interval. We don't have a point over here to the right of 7, and we don't have a point over here to the left of -1/2. So what I want to do then is I want to remember the simplified version of this function. Let's say g of x equals 1 over x minus 7. So what you can do here is you can pick a value that is in this interval here, and let's just say -1. So when you find g of -1, you get -1/8. So that point would be, let's see, -1/8, -1/8. I don't know, right about there? Sure. We have to pick a point, we have to pick an x value over here to the right of 7. I think I'm going to pick g of 8. And when you figure out g of 8, you'll get 1, right? 1 over 8 minus 7, that's 1 over 1 is 1. So you've got another point over here. All right, and then I think we are good to go for graphing. So we have a point in every single interval. We can start drawing the asymptote hugging curves. Let's go up like this. Yep. Come down like this. All right. And then we can draw the asymptote hugging curve over here. Fine. Something like that. The last thing that needs to happen here is that you've got to go back and put your hole in the graph. Because there is a hole for this function, you've got to go back and put your hole in the graph. What is the location of the hole in the graph? Well, it happens at x equals -1/2. So for graphing purposes, I just find x equals -1/2, I don't know, right about here somewhere. And you're just going to draw an open dot on the graph at that point. That's how you put a hole in a graph. You just have to find the x coordinate and then draw a little hole on the graph. Pretty simple. So there's the graph of g of x equals 2x plus 1 over 2x squared minus 13x minus 7. One more example. Here it is. Go ahead and pause the video, see if you can find all of the things. Remember, you'll want to do the restrictions in the domain first. Then you'll want to go through and do the intercepts, the horizontal asymptotes, and then you'll want to find out if there's any symmetry for this function. Yeah, here's everything. It's a lot of information. All right, first thing, restrictions. We have vertical asymptotes, no holes, and here's the domain. Again, you'll want to make sure you factor everything in the numerator and denominator so you can find out where all of these restrictions are, where the holes are, and then if you can, you want to simplify this function like we did in the last example. Second thing, x-intercept is 0. If you set the top equal to 0 of the simplified function, which is this, if you set the top equal to 0 and solve for x, you get the x-intercept of 0. The y-intercept, also 0. If you find h of 0 here, you put the 0 in the numerator, 0 in the denominator, you get 0 over -16. That's fine. 0 over anything is 0. So you're allowed to have that. The horizontal asymptote, this function is bottom heavy, so the horizontal asymptote is y equals 0. And the symmetry here, this graph actually has some symmetry to it. If you find the h of negative x, I apologize for that, this should be h of negative x, then you can substitute negative x in for all of the x's. The top, every term in the numerator changed signs. That's what makes the numerator odd. No signs of any terms in the denominator changed, right? It's a positive x squared minus 16 in the original. You get a positive x squared minus 16 after you substitute negative x in. And that makes the denominator even. Whenever you have an odd function over an even function, or vice versa, an even function over an odd function, that means the function is odd, or that means the function has symmetry about the origin. So let's take a look at the graph of this. All right, final slide for the video. We've got everything plotted over here, all of the important stuff, the vertical and horizontal asymptotes, the x and y intercepts. We know the symmetry is odd, and we have the domain up here. And remember, you have to have one non-x-intercept point graphed in each interval of the domain. Well, okay, I mean, we have to actually go through and figure out some points here, because the only point we have is an x-intercept point. So we have to figure out 3 different points to make this work. Or maybe 2. Let's see if we can use the symmetry to our advantage. So remember, the function is negative 4x all over x squared minus 16. So I can pick any number as long as it is not a restriction or an x-intercept value. Okay, so how do we do this? We have to make sure, let's see, maybe we can start with negative 6. I'll tell you what, I like positives. Let's start with positive 6. Let's see what happens there. So we would say h of 6 would be negative 4 times 6 all over 6 squared minus 16. And that ends up being negative 24 all over, what is that, 20? Which is, so you can divide everything by 4. You get negative 6 over 5. This is about 1.2 with a negative in front. So this point here would be plotted at 6 comma negative 1.2. And right about there. Well, let's see. Let's move over to the middle one. The middle interval here. I can pick any number I want in this middle interval as long as it's not 0. So I'm going to stick with a positive number. I'll find h of 1. So let's do that. H of 1 is, let's see, negative 4 times 1 is negative 4. That's what the top would be. And let's see, negative 1 squared minus 16 is minus 15, or 4 over 15. So the x value is 1, the y value is 4 over 15. So that ordered pair is, let's see, 1 comma 4, right about here. All right, now there's a lot to be said about this. Because we know the symmetry of this function, I can tell you that if you, well, the symmetry is odd, we can change both signs of this ordered pair. So from 6 comma negative 1.2 to negative 6 comma 1.2. Negative 6 comma 1.2 is right about here. So we get that point for free because we know the function is odd. Very similarly, we're here, that is 1 comma 4 over 15. if you change the signs of both of these both coordinates of this ordered pair, you'll get -1 comma -4/15 right about here. And we have all the points we need to graph this rational function. Oops. So I'll start drawing the asymptote hugging curve for that branch and this branch. The outside branches are pretty simple. But then we have this inside branch that does something real crazy. Off to the left, it's going to go down. Again, if there are any points that you've plotted in the same interval, they all have to be connected. So all of these 3 points have to be connected. And then to the right, it goes up. Pretty straightforward. But you see what's going on here. This graph crosses the horizontal asymptote when x equals 0. You haven't seen that yet. Why does that happen? Well, this will happen only in cases that you have a bottom-heavy function, which gives you a horizontal asymptote of y equals 0, and you have an x-intercept, like this one here. So how do you know? Will it cross the horizontal asymptote? Will it bounce off the horizontal asymptote and come back down? How do you know where that is supposed to go? If you go back and look just at the numerator, we're going to bring back some math that you've seen relatively recently. The numerator is -4 to the -4 times x. There we go. And if you set this numerator equal to 0 and solve for x, you'll notice that there's an exponent on this x, and it is 1. When you solve for x and you get x equals 0, this has a multiplicity of 1. And whenever you have an odd multiplicity, the graph will cross through the x-axis. So I think it's really neat that we get to bring that back. You say, this isn't a polynomial. Well, the top is a polynomial, so we can still think of the zeros of that polynomial that same way, with multiplicities. Will it bounce or will it cross? And that's it. That concludes the lesson for rational functions and graphing rational functions. It's not completely in-depth because there's a lot more to it, again, that will normally get taken further in a pre-calculus course. So that being said, I hope this made sense for everyone out there, and I wish you luck.